Assalamualaikum and a very good evening to all. My name is Siti Fazila Nuraim Beti Sidi Omar, and today I'm going to present to you my research progress for electronic and thermoelectric properties prediction of hexagonal perovskite Ba2CoTeO6 based ceramics. My supervisor name is Dr. Nohafiz Binti Burham, and I am semester 4. Executive summary. Bismuth telluride has the base figure of merit set T for thermoelectric devices reach 1. Alternatively, research has been done to reach a practical thermoelectric material that reaches ZT at least more than 1. However, the exploration of new material and lower costs within a short period is very challenging. Therefore, more research is necessary to be done in thermoelectric module and a computer program that uses finite element analysis, thus increasing the accuracy of prediction of the performance. Why I choose perovskite material? It is shown that oxide material is becoming more critical as it is found to have a high temperature durability, non-toxic and environmentally being nature, and low cost of raw and processed material. Example, BCTO is a hexagonal perovskite with antiferrometric properties in its structure. Secondly, some Ca2FeMO6 CFMO studies show that the material can have a high potential for thermoelectric conversion material in which low thermal conductivity can coexist with high electrical conductivity. And the third one, SRTiO3, which is a promising N-type oxide semiconductor for TE energy conversion. This material has a high chemical and thermal stability, environmental compatibility, and low toxicity. Based on the summary, the objective of my research was, first, to analyze the electronic and thermoelectric property of oxide perovskite SRTiO3 and Ca2FeMO6, and the second objective is to express the ability and possibility of as a credible thermoelectric material in terms of figure of merit. The first result, 3 different materials was chosen, which is bismuth telluride, Ca2FeMO6, and SRTiO3. The table below shows the Seebeck coefficient, electrical conductivity, and thermal conductivity of the 3 materials. All these materials are temperature independent. The simulation was done in a COMSOL Multiphysics software, and the geometry that was generated is as in Figure 2, which shows a single leg geometry sandwiched with a copper electrodes. For the result, we took temperature distribution, electrical distribution, and temperature versus current. As you can see in the temperature distributions, is 3 different materials produce a 3 different distribution in the geometry. And for the electrical distributions, we injected a current of 0.7 ampere at the bottom of the geometry lake, and you can see the distribution of the electrical potential. The distribution then is extracted into a graph, as you can see below. The temperature distribution, you can see that 2 of the perovskite material, SRTiO3 and CFMO, show a heating effect, while bismuth telluride show a cooling effect. For the electrical distribution, both of the perovskite produce a high voltage to drive a 0.7 ampere. This is due to the higher electrical conductivity of the perovskite material. Lastly, temperature versus current, we can see that CFMO given a highest temperature difference in each different current. This is due to different material property, which is CFMO is a high temperature material, while SRTiO3 and bismuth telluride is a low temperature material. For the conclusion, the simulation result revealed that bismuth telluride acts as a p-type thermoelectric element and potentially used as a Peltier cooling effect. However, both the perovskite material act as an N-type thermoelectric element with a heating effect. Thus, computer simulation, such as COMSOL Multiphysics software, thus can help to explore, predict, and evaluate conditions for other new TE material. The second simulation was done in a geometry of a TEG with two legs. The top part of the geometry, you can see that I introduced a temperature difference of 300, 400, and 500 Kelvin, while the bottom is a cold side temperature, which introduced a 0-volt ground and a cold temperature of 273.15 Kelvin. As you can see in the table on the right is a material property of thermoelectric material for the P-type, N-type, copper, and alumina. The boundary for this simulation is the temperature difference in the thermoelectric generator was measured using a heat transfer model. All surfaces are adiabatic except the hot and the cold junction surface. As a result, convective heat transport was not taken into account in the simulation. For the thermoelectric model, a steady-state condition was assumed. The first result was the temperature distributions. As can be observed, the thermoelectric material substantially impact the temperature distribution. Bismuth telluride has a higher thermal conductivity, thus it shows a smaller temperature gradient resulting in a low percentage of thermoelectric converted energy. As you can see in the picture, an example of the temperature distribution with the hot temperature at the top and the cold temperature at below, and the graph, as you can see, bismuth telluride has a smaller temperature gradient. The second result is the electrical distribution. Since thermoelectric elements are thermally coupled in parallel and electrically connected in series, voltage potential fluctuates from one end of the model to other. Different voltage output obtained depends on the material property. Bismuth telluride generates a negative voltage, while SiO3 and CFMO generate a positive voltage. Based on the literature, it said that it has a little effect because polarity of voltage can be changed simply by flipping the application connectivity. Table below shows the voltage that was produced by hot temperature of 500 Kelvin and load resistance of 200 ohms. And we can see that SiO3 produces a higher voltage than the other two materials. And we can also see that CFMO has a relatively low result due to its material performance having a low value of ZT at low temperature. Next result was the electrical performance analysis. So load resistance has shown that it can have a significant effect on the thermoelectric model output. So to observe the effect of the power output on different load resistance, the load resistance was varied from 0 ohms to 20 ohms. And the hot side was set to 300K, 400K, and 500K to observe the effect of temperature difference on power output. And the simulation data was tabulated on the right table. Based on the data, as the temperature increased, the power also increased. It is noticed that as the load resistance increased, the power output also increased, but initially, but then it declined drastically. This is due to the maximum power transfer theorem (MPTT), which maximum power was achieved when the load resistance is equal to the internal resistance. However, when the load resistance is greater than internal resistance, the magnitude of the power output will decrease, since the total circuit resistance becomes huge. When comparing between three materials, SiO3 has a higher power output. It can be seen that the power increased with increasing temperature difference. Thus, this opens up the possibility using material in higher temperature TEG drivers. Lastly, for the electrical performance analysis, the Imax and Pmax of the material can be calculated and plotted with different hot temperature value using the below equations. Each material is plotted power versus current, as you can see in the slide below. It can be seen that the maximum power output increases in a polynomial trend as current increases. Thus, we can say that Pmax increased for a higher thought temperature value. Conclusion for this simulation is all material exhibit a similar graph pattern, but the result varies between the material. And we can see that SrTiO3 generates more power and voltage. Perovskite material has potential to be used in TEG devices. Next, I'm going to talk about my status of data collection and analysis on my research. So, both of the simulation of the single leg TEG and the pair of TEG for 3 different materials has been completed. I'm working now on a single leg TEG Seebeck effect. Next is the list of my publication which I have completed is the first paper, Simulation of Heat Transfer Response on Single-Leg Thermoelectric Material Behavior, which was published in a Transtech Publications in the year 2022. The status of my thesis writing, as we can see, I have started writing on my chapter 1, 2, 3, and 4, which most of it are almost 50% completed. What's next? I will continue with designing and optimizing TEG and completing my paper on electrical performance of single thermoelectric with different types of material using multiphysics simulations. The publication is the IEEE ICSE 2022 and the status is accepted with corrections. Thank you.